Here's another example of how you work with Newton's second law, F equals ma, to solve different kinds of problems. And this time, we're going to look at what we call the Atwood machine. And you may say, oh, what's an Atwood machine? And actually, all it is just a simple pulley. I don't know really why they call it Atwood machine. Maybe that's the person who figured out how to use a pulley like that. Don't really know. And let's read the problem so we can go ahead and try to solve this. It says here that a string is placed, oh, I need a D here, it's placed over a massless and frictionless pulley, also known as an Atwood machine. A mass of 8 kilograms is suspended at one end, while a mass of 5 kilograms is suspended from the other end. What is the acceleration of the system? All right, let's go ahead and make a little drawing of that. So let's say we have a ceiling. From the ceiling, we suspend the pulley, and then we put a string over the pulley. And on one end, we'll put a mass, let's call it mass 1. And at the other end, let's have another mass called M2. You can see mass 1 is bigger than M2. So let's say the mass 1 is equal to the 8 kilograms listed, and here mass 2 is equal to the 5 kilograms. All right, since there's no friction, and the pulley has no mass, of course, there's no such thing as a pulley that has no mass and no friction, but in physics, to make things a little bit easier, that's what we start off with. Now you look at this and go, okay, where do I start? Well, the best place to start is to draw all the forces acting on the system. Now, the easiest way to do a problem like this is to only look at forces acting on the system from external sources, not within the system. We do realize that there's tension on the string here, and there's tension on the string there, and if there's no friction on this pulley, and the pulley has no mass, then the tension on both sides will be exactly the same. So we then realize that on the left side, we have gravity pulling down with a force of m1g, which is the weight of object 1. And on the right side, we have a force pulling down, and this is m2g. I forgot the 2, let me put the 2 in there. So this is m2g. All right, and those are really the only two external forces on the whole system. Now, because of the pulley redirects the direction of the force. So here we can see that m1g is pulling down this way, and m2g is pulling down this way. So it's kind of a tug of war between the two forces. And if m1g is bigger, then the whole system will accelerate this way. If m2g is bigger, then the whole system would accelerate this way. Now I think it seems easy to see that m1g will be bigger than m2g, so we can assume that there's going to be an acceleration in this direction. Now using the equation F equals ma, we then realize that the acceleration will be equal to the force applied divided by the mass. Now in this case, there are two masses and there are two forces. So we want the net force acting on the whole system and the total mass of the system, because the net force will act on both masses, so we have to account for both masses. So we'll call it mass total. Now what is the net force in this case? Well, we have the m1g, which is in the same direction as acceleration, which will cause an acceleration to happen. m2g is fighting back in the opposite direction, so it's opposing the acceleration. So we think of that as a negative force, or the force in the opposite direction. So we need to subtract this force from this force to come up with the net force. So that means that the net force will be equal to m1g, aiding the acceleration, minus m2g, opposing the acceleration. Then you say, well, what about the tension on the string? Doesn't the tension pull on the masses as well? And you're absolutely right, those tensions do. But since the tension is within the system, as part of the system, the way we solve the problem here, we do not need to worry about that. Only the outside forces, the external forces. The next time I do this problem, I will actually do it where we have to take in account all of the forces acting on it. But this is definitely the easiest way to do this problem. So we then take that net force and divide it by the total mass. And the total mass would be the sum of the two masses, m1 plus m2. So here we have the net force divided by the total mass. That will give us the acceleration of the whole system. Well, let's plug in the numbers that we have. Or actually, we can first maybe factor out the g, makes it a little bit easier to work with. So this is m1 minus m2 times g. So I factored out the acceleration of gravity. I go m1 plus m2, like so. All right, plugging in the numbers. since m1 is 8, so that's 8 kilograms. And I should put it in parentheses like I did before, so 8 kilograms minus 5 kilograms times g, which is 9.8 meters per second squared. And we take the whole thing and divide it by the sum of the two masses, which is 8 kilograms plus 5 kilograms. All right, we can go ahead then and simplify it a little bit more. So we have the acceleration is equal to 8 minus 5 is 3. So that gives us 3 kilograms times 9.8 meters per second squared. In the denominator, we have 8 plus 5, so it gives us 13 kilograms. Notice that the kilograms cancel out. And now we grab our calculator, calculate the result. So we have 3 times 9.8 divided by 13 equals, and so we get 2.26 meters per second squared. So acceleration is equal to 2.26 meters per second squared. Now, however, notice that you were given the masses to just one significant figure, which means your answer should only have one significant figure. So we really should write this as a is equal to 2 meters per second squared to match the significant figures of our original problem. That's how you find that. Now, one more thing. What if we wanted to calculate the tension in the string? And so let's call this tension 1 and tension 2, assuming for a moment that they're not the same, although we already know that they're supposed to be the same. Since tension 1 is a string that's attached to the mass that's accelerating downward, we can say that tension 1 is equal to the weight that it must hold up, which is the weight of the object, mg, in this case m1g, and then it would be plus or minus the force required to accelerate this mass. And so the force to accelerate the mass at acceleration of a equals to 2 or 2.26 meters per second squared, it would be the mass times acceleration, so it would be m1g plus or minus m1a. Now, which way is it? Is it plus or is it minus? Well, if you were to accelerate the object upward, you would need additional force beyond that required to hold it up against gravity, so then it would be plus. But if the object is accelerated downward, then you don't need as much force to hold it up against gravity, because you're allowing it to accelerate downward, then it becomes minus. So in this case, since m1 is accelerating downward, the answer is it becomes a minus. So this becomes minus m1a. To find the tension on the other side, tension 2, again, it would be the weight hanging down from that string. The weight of the object is m2g, and then plus or minus the force required to accelerate that, so it would be m2a. Now in this case, we realize that this mass is being accelerated upward, because acceleration is in this direction. That means in this case, it would be plus m2a. It would require additional force. All right, now we go ahead and we plug in the numbers. So this is equal to m1g. m1 is 8 kilograms, so this would be 8 kilograms times 9.8 meters per second squared, minus m1, which would be 8 kilograms times 2.26. And I'll, just so that I don't make a rounding error, I'll use a more accurate number, 2.26 meters per second squared. And if I now grab my calculator, I already have it in my hands, so let's do that. So it's 9.8 minus 2.26 times 8. Oop, let me do that again, something didn't work. 9.8 minus 2.26 equals, and then multiply times 8 equals, and we get 60.32. So this is equal to 60.32. And of course, since tension is a force, the units in this case are newtons. And notice the units, kilograms, meters per second squared, is indeed the units of newtons. Doing the same on this equation, and I need to draw a line there so we don't confuse the two. So the second mass has a mass of 5 kilograms So times 9.8 meters per second squared, plus, again, 5 kilograms. In this case, the acceleration here is also 2.26 meters per second squared. If I now calculate that result, so we get 9.8 plus 2.26 times 5, and also here we get tension 2 is equal to 60.3 newtons. Now my calculator says exactly 60.3 newtons. That's because I rounded off my acceleration result to 2.26, and so there's a slight difference between the two, but that's just simply a rounding error. So you can see indeed, ignoring the rounding error, that tension 1 equals tension 2, meaning the tension is the same on both sides of the equation. Okay, I will now go ahead and do the very same problem again, but using a different way of doing it. All right, so tune in for the next one.